Nice. So this paper, I mean, this presentation is a little bit different than ones that we've done before, and it's because I'm actually going to be talking about a concept from a paper instead of talking about a paper. If anyone was here a couple of weeks ago, what I decided to do is take a paper that was pretty influential from about 10 years ago about training models using Langevin dynamics, read it, and then go through papers that it cited and concepts that it cited that I'm unfamiliar with. And one of the concepts in that paper was Fisher information. So I decided to do a presentation today about Fisher information. I don't know how long it's going to be. Could be a 10, 20-minute presentation. We'll see. Maybe longer. Of course, feel free to ask questions. And let's get started. So before I start this presentation, I just wanted to put a disclaimer in, which is that I think there's one slide where I do this, but for most of the slides, I'm talking about like theorems or results of theorems. But I'm not talking about the conditions under which they're true, because everything you see here, it's like, if this function follows this, has this property, then it's true. There's a lot of that in the math behind this, which I'm not talking about, because I'd rather focus on the results than going into a lot of detail about the conditions, which I think could just be confusing. And my end goal for this whole presentation is actually that you take one thing away about Fisher information and then have like a general idea about it, which is like one deep thing away about Fisher information, and then have a general idea about other stuff which might be important, or which is good to know. So why are we talking about Fisher information? Like I said before, it's in this paper that we looked at. What is it in this paper? Where is it mentioned in this paper? I just took that out here. So this paper, for some context for people who weren't here before, is about training a model, a neural network, like doing deep learning, or actually, it's not even deep learning. It's like doing gradient descent to update, to train a model to learn its parameters, and then like taking a Bayesian approach towards the towards training the model at the end. And so a lot of the paper is about like, how do we train the model? How do we update the parameters? And there's a component of it which is called which is step size. Like that's a component of the algorithm, deciding the step size at each point. And that's where this comes in. It says we can now relate the step size at the sampling threshold to the posterior variance via Fisher information, which is related to VS, which is the empirical covariance of the scores via this, and to the posterior variances. So I won't go into any more detail. You don't really, that probably just sounds like a ton of jargon to most people, and it should. But there's more. But the key things to, like, the key thing that I look at when I see this is I notice like, okay, Fisher information is related to posterior variance. Like, how is Fisher information related to variance? That's the thing I thought I would look at. I actually don't. Yeah, what's the connection between Fisher information and variance? We'll go into that later. But before that, what is Fisher information? Because it's just mentioned here. And for me, I was like, I have no idea what this is when I saw it. So what is Fisher information? Okay, the Fisher information, this is from Wikipedia, is a way of measuring the amount of information that an observable random variable x carries about an unknown parameter theta of a distribution that models x. So it's telling you, the Fisher information here is saying, it's trying to tell you how much information you can get from the distribution about what that parameter value is. It's the first time we'll say that, but it's not the last, so let's keep going. And formally, it is the variance of the score or the expected value of the observed information. So I just put this out here because if we go back, you'll notice that IF is Fisher information, and it's equal to n times the empirical covariance of the scores. So you can see already that like this is just taken directly from the definition of Fisher information in the paper. Okay, so like a key part of this definition is like the amount of information that an observable random variable X carries. So I wanted to just touch on what is information in probability theory. What is information is actually an incredibly deep topic if you try to go down the rabbit hole of like Wikipedia articles on it. But I chose one part of the definition of information on the page about it. And it's that the definition is any natural process that is not completely random and any observable pattern in any medium can be said to convey some amount of information. So, like I said, the discussion of what is one sec. Okay. The discussion of what is information, for me, the component, the part of this whole idea that I wanted to, or this concept that I want to bring out is, well, two. One is pattern versus randomness. And that's kind of, I think, more of like a physical view of information, where like if something is completely random, then you could view it as having no information, or like you have no idea what's going to happen because everything is likely in the space of events that's possible for like some kind of physical process. For example, like whether a photon is going to be absorbed or not. I think depending on the material, the likelihood of that is 50-50. And if that's the case, that's a completely random event. And there's no pattern. There's no bias. So one way you could think of it, what is information, it's like whether there's a pattern that's being displayed or how random is something. And so that's the physical way of thinking about information. But then there's the like information theory probability way of thinking about information, where you flip this and you, instead of saying like pattern versus randomness, you think of it as uncertainty versus certainty. So like a probability distribution, I just want to make sure that my next slide. Okay, yeah. A probability distribution, it describes a space of events. So like I said before, one could be whether a photon gets absorbed by a material or not, or bounces off of it, is like, say that's a 50-50 chance. And the two events that can happen there are the photon gets absorbed or the photon bounces off the material. Another one could be like, I don't know, what's a good one? When, I don't know, how many white cars you're going to see in a day, you know, that there's a probability distribution around there where there's like probably the minimum is 0 and the maximum is, I don't know, something like 100. But in all of those cases, there's a space of events which can be infinite or finite, and the amount of certainty you have about like if you sample this space of events, like what the actual event will be. So like maybe you're always going to see 5 white cars in a day. Then you have complete certainty about that, and the idea is you have complete information if you're using like the idea of information and probability theory. So and one of the reasons why I bring this up, which is kind of an aside, is that that's actually how people apply probability to decision theory. Instead of viewing instead of viewing that the reason why we use probabilities is because events are random and we can't predict them because of this randomness, it could be that a situation is completely deterministic, but we don't have the information to know what's going to happen. And with our limited information, there's uncertainty. And so we use probabilities to describe that uncertainty. So in terms of Fisher information, what it's really saying is like, when it's saying measuring the amount of information that an observable random variable X carries about an unknown parameter theta, it's saying how certain can we be about theta given the probability distribution that it's modeling? And we'll go into that because it's a kind of, if I were to hear that for the first time, I find it a bit confusing. But anyway, so when we're measuring uncertainty in probability theory, so measure, and literally, if you look at books, they'll say measuring uncertainty, and then they'll start talking about like measuring information. So it's pretty interchangeable in books. Usually, we use this like Shannon entropy, which is the negative of the sum of the log probability of x times the probability of x, where you're summing over the event space. If it's infinite, it would be an integral. Yeah, go ahead, Arvin.
Sorry, it's just this is one of the cases where you can't easily change this to infinity.
Okay, go on.
Everything breaks essentially. So
okay.
Keep it discrete.
Okay. Thanks, Arvid. But yeah, so this is the way that for discrete probability distributions, they measure entropy. You can measure entropy for continuous ones, but I think, as Arvid pointed out, it's not just like put an integral in there. Anyway, like I think the entropy of a Gaussian is its variance.
Yeah, but not quite. And the weird thing is it can become negative, and it breaks some of the very basic assumptions that you typically make about entropy. Which is really, really weird. Yeah.
Thanks. But anyway, so this is the way that you measure entropy, or actually like the information content of a distribution for discrete distributions. And just to give you a quick example, I made like a 2-event space probability distribution where you have like 3 different versions of it. Like this is a distribution where one event has a 25% chance and one event has a 75% chance. Then the second one is 50-50, and the third one has a complete certainty. So only one event is possible. And you can see is like as the entropy decreases, that's basically saying the uncertainty decreases, and you're more likely to get a single event or a subset of them. And you can see here that like the most uncertain event, the one with the least information, is the one that's each event is equally likely. Yeah. So yeah, as I said, but I just wanted to go over that maybe in too much detail. But so what this is, Fisher information is really doing is it's measuring the amount of certainty we can have about a parameter theta given the distribution that it's that it's describing, and for a random variable. Yeah.
So I have a question. So this parameter theta.
Yeah.
So in your previous example of these 2 event distributions, what would be the parameter here, or is that a way to say it then?
Yes, that's a good question. So the parameter would be that literally the probability of, since it's a 2-event space, you can describe it with one parameter, which should be like the probability of one of the events. So say you're just doing the probability of the first event, it would be, and we'll call it theta would equal 0.25 for this case, theta would equal 0.5 for this case, and theta would equal 0 for this case. So it's the probability, it's the parameter that describes the distribution.
Okay, so I'm guessing there could be multiple of such parameters to describe a distribution. And does that mean the Fisher information can tell you the uncertainty of any of those given parameters? Is that like a method of doing that?
Yeah.
Okay, that makes sense.
I don't think it's, I mean, there's certain assumptions. Like I said before, I'm not going to talk about like what are the things that have to be true about the distribution for this to be true. But yeah, that's generally true. Okay, we talked about that. So I just wanted to say some of the use cases of the Fisher information, so it doesn't seem like this completely abstract concept. So the Fisher information matrix is used to calculate the covariance matrices associated with maximum likelihood estimates. So that actually comes up in the paper. Actually, no, they're using it for Bayesian statistics, sorry. But so there's a relationship between the Fisher information matrix and covariance matrices and maximum likelihood estimates. Then it's used as a formulation of test statistics, such as the Wald test. In Bayesian statistics, the Fisher information plays a key role in the derivation of non-informative prior distributions according to the Jeffreys rule. So that's a pretty cool. I know a little bit about non-informative prior distributions, and I think that's a cool element of Bayesian statistics, actually. And then finally, the one that's related to ours, which is that in Bayesian statistics, it also appears as the large sample covariance of the posterior distribution, provided that the prior is sufficiently smooth. So that's actually where we're seeing it in this definition. Where is it? Over here. Because the posterior, it's also equating the posterior variance to the inverse of the Fisher Fisher information in this like part where my cursor is. That's what it's saying, and that's another result, which unfortunately we won't have to be able to go into now. But yeah, so that's one of the applications of Fisher information that is in this paper. Okay. Okay, so I wanted to talk about how samples provide information about theta. So right here you have two distributions. One is has a much larger uncertainty than the other. And you can imagine if you're sampling from the distribution that has a higher standard deviation, that your samples will be centered around the mean, but more spread out. And so from that perspective, it could be harder to actually estimate the mean, or it would take more samples to estimate the mean exactly than a distribution that has a lower uncertainty, like a smaller standard deviation. So that's one of the key ideas of what's going on here, which is when you sample from a distribution, it provides you information about the parameters of that distribution. And so, yeah, that's what's going on with Fisher information. I hope that explanation gives just imagine you're sampling from one of these and you're trying to estimate what the mean is. I hope that gives you an idea of why there's such thing as Fisher information, because there's uncertainty based on the samples that you get. And yeah, so if we go back to the definition over here, yeah. It says formally, Fisher information is the variance of the scores. Is variance of the scores. So what is a score? Because that's actually a really important concept in diffusion models as well. But funny enough, actually I'll go into that later, so I won't say anything about it. But if we let f of x given theta, or f of x theta, be the probability density function describing some probability, some random variable x, then the score is the derivative with respect to the parameter theta of the log probability of x. That's what the score is. Yep. So why is it called the score function? That was my first question when I heard it, because I was like, this seems like why it sounds like a sports reference or something. And it actually turns out that the guy who maybe not discovered Fisher information, but the guy who really developed it, who's Robert Fisher, he pioneered the use of the term because he actually had a lot of different scoring functions he would use to choose what was the best distribution. And the one that he liked the most was the derivative, our definition of score. So this definition of score he would call the ideal score. And then in subsequent literature, they just started calling this the score function for probability distributions. But yeah, it's called the scoring function because he would literally use it to score different probability distributions that he was trying to decide between in his research. He was a biologist as well, so he was trying to decide things about samples of biological properties of people or genetics and stuff like that. That's where he was using his statistics. So one important result about the score, which is underlying Fisher information, is that if you take the expected value of the score, I wish I could, maybe I should have replaced this with g of x so it doesn't look so complicated. But imagine in here you're taking the expectation of some function, a given theta. So at the true parameter value. So when you're like estimating the score of a function, of a probability distribution, and you know the true parameter, then the expectation is equal to 0. So that actually kind of makes sense to me, because if we were looking at this not as a probability distribution but just as a function, oh, go away. Sorry. If you were looking at this as just as a probability, as a function, and not as a probability distribution, like when you get to your local minimum, so which is what I would, or I think in this case local maximum, when you get there, you actually it would be global for the anyway. So when you get to that point, the slope should be 0, and the scoring function is literally a derivative or a gradient if the theta is more than one value. So it's saying like, okay, when you get to when you're estimating the gradient at the true value, it should be 0 because it's the best value for the log likelihood and the likelihood. So that makes sense to me. But when I was looking at, maybe this isn't confusing to you guys, but when I was looking at this, I was like, how can the score function have an expected value? And I don't know why it created such a block in my head, but it took me a long time to figure out that it has an expected value with respect to the original distribution. So that's why I was saying, when you're taking the expected value of the score, this thing here, it's like you're taking the expected value of it with taking into account like the probability density function, the original one. And then here's like, if you calculate that integral, if you want to write out that integral, what it looks like, it looks something like this. One challenge for anyone is if it test of their how well they remember basic calculus is like, how do you get from here to here? Because I also had to stare at this 3 times before I could see. Because if you notice, this is the log, and there's no log here. But anyway, if you remember your basic, if you remember like the chain rule with calculus, you'll get there. But anyway, so it's the expectation with respect to the original probability distribution, and but one of the results underlying the Fisher information is that at the true parameter value is equal to 0. Okay. And then and then as we said, the Fisher information is the variance of the score. It's actually the variance of the score at the true parameter value. So if you know the true parameter value, then you calculate the variance, then you get the Fisher information. And here's where it gets, this is the thing that I wanted you guys to learn, what I've written here, where it gets non-intuitive to me. So high variance in the score function means low, this should be low, yeah, this should be low uncertainty. Sorry, I definitely want to correct that. Low uncertainty, and low variance means high uncertainty. Yeah, at least I wrote the second part correctly. So high variance in the score function means low uncertainty in the parameter, and low variance in the score function means high uncertainty in the parameter. So actually that means like when the Fisher information is high, actually, yeah, that makes sense. When the Fisher information is high, you can be more certain about the probability. Did I use the charger things? When the Fisher information is high, or the variance of the score function is high, then you can have a good idea of what the parameter is given its distribution, and when it's low, you have a bad idea. The reason why I think that's unintuitive, because usually I think higher variance means higher uncertainty, which means you know less. But in this case, it's higher variance means more uncertainty, so you know more. So why is this the case? Again, we have a low variance distribution here and a high variance distribution here. And so one thing to remember about the score function is if we go back, just highlighting it again, it's the derivative or the gradient with respect to the parameters of the log likelihood function. And if you have a low variance, what that means is that the gradients around the distribute, like the correct, like the true parameters log likelihood are quite small. Like they don't change that much. And what that means is that if you want to have like a big difference in the log likelihood from the true parameter, you have to take a big step in changing the parameter. So say like your mean is 0 and you have like very small scores around it. That means that if you want to change the log likelihood from its best value of 10 to like 12, you'd actually have to, yeah, go ahead, Arvin.
Yeah, one picture that helped me understand was going into the potential well that you painted earlier. The variance is roughly how curved the well is at the bottom, right? So if the well is a very high variance, then the curvature is very, very high, and the well essentially gets very, very deep. Whereas if it's low variance, the well gets flatter and flatter, and so the range of possible values just becomes bigger, and that's your uncertainty about the parameter, not about the score function.
Yeah, there you go. Couldn't have said it better myself. Thank you. So yeah, I have a couple of slides that are just trying to explain what Arvid said, but he said it better. So I'll just say, like, the way my final conclusion from that is like, if you have low Fisher information, that means that even if like when you're trying to estimate the parameters given the distribution, like the true parameters get really hard. Like you could have a big error in your parameters just from sampling from that distribution, because it's hard to tell what the parameters are given the distribution. Versus if you have a high Fisher information, it's much easier to tell what the parameters are. Now, okay, just two things quickly and then we're done. But again, where does this posterior variance come in? So like, how come, if you look where my cursor is, how come the posterior variance is like equal kind of to the inverse of the Fisher information? Now, I don't have time to go into this, and I didn't even have time to prepare to go into it. But there's this thing called the Bernstein-von Mises theorem, which is where where I'm guessing Bernstein and von Mises, or if this is one person, then that person was able to show that like for maximum likelihood estimates of theta, the covariance matrix can be given by this value here. So if you're interested in figuring out how those two are related, Bernstein-von Mises theorem. And then one final thing I just wanted to highlight is, do I have it? Yeah, okay. So if we go back, sorry, to this. So as we said before, the Fisher information is the variance of the score. This is one way of describing it, where you can see it's the expectation of the score function squared, which is the variance. But you can actually prove with a pretty small proof that it's the Fisher information is also equal to -1 times the second derivative, like, or the derivative of the score function with respect to the parameter again. And so what that means is that if in the multivariate case where there's multiple parameters to your distribution, you can define that Fisher information this way, and it becomes a matrix because you have to take the second derivative with respect to every combination of parameters. And so that's why it's called the Fisher information matrix. These last two I just included as like FYIs, so you know about them. The main takeaway that I'm hoping you get from this is that high variance in the score function means low uncertainty in terms of estimating the parameters, and low variance in the score function means high uncertainty in terms of estimating the parameters. And yeah, that's the presentation. I hope you guys found it interesting and useful. Any questions? Yeah. If anyone has any questions, go for it. Okay. If not, thanks everyone for coming. Next week, Gerard is going to be presenting DeepSeek's R1 for those who are interested. And I'm actually thinking about next time I present presenting a paper that's a deviation from this, because I saw this new architecture that came out of Google that sounds interesting called Titans. But maybe I will present a paper. I mean, I'll present another set of concepts from this paper. I'm definitely not done with this. But anyway, thanks everyone for coming, and I hope to see you guys here next week.
Thank you.
Thanks, Peter.
Thank you very much.